Hello.
Hi.
How
Hi.
are you?
I'm good. How are you?
I'm doing fine. How was your 3-day weekend going so far?
Um, it was pretty good. I went to um San Francisco and I tried out this cool like Wingstop place. It's like Wingstop
Oh,
and waffles.
mm-hmm.
Um, and then I also like went to this like cool cars and coffee. And it's not cars and coffee, but they're like cars inside this coffee shop.
Oh yeah, I think I saw on your story.
Yeah,
Yeah,
it
oh my
was pretty
gosh.
nice.
Uh-huh.
And then also went to like go take pictures off of on Mission Street or like
Mm-hmm.
Powell. So it was pretty nice.
Yeah,
How
that's
about you?
good. I went to eat hot pot with my friends in
Mm,
chiropractic school. It
yum.
was pretty good. And then we went to like a coffee shop with like a bunch of tables and just like went there, try out the drinks, and then
Mm-hmm.
like talked there and like did some work there. The rested a lot, and yeah, it was pretty nice.
Yum. That
Yeah.
sounds hot pot.
Mhm.
I'm gonna be honest. Like I've always seen hot pot, but I've never actually tried it.
Oh yeah, like I like was the most inexperienced like person there to go hot pot. So
Really?
my friends like they all went to hot pot more than me, so I like they had to
Wow.
like guide me on like
That's
how to eat
funny.
it.
That's
Yeah.
funny. Yeah.
Uh-huh.
I'll learn too. Hopefully
Yeah.
someday.
Mm-hmm. Yeah. Hey Layla, how are you?
Hi, I'm good. How are you?
I'm doing fine, doing fine. You're also from 118B, right? Helix this quarter?
Yes.
I see. Yes. So we could focus on that. Did you guys have any questions or problems that you guys wanted to start off with for today?
I did come back with that one problem that you gave me.
Oh,
I'm
yes.
not actually sure if I did that right, and
Uh-huh.
I did not submit it as a PDF.
Yeah, yeah, it's
I did
okay.
have it as a screenshot, but I put it under Discord.
Yeah, I see it. Yeah, that's okay. So I see what you did right here. We had this structure with the alkene methyl group right there, and we want to synthesize it into this alcohol over here at this last subcarbon. So I see what you did. You put it as only one step, and you drew the arrow pushing mechanisms with the reversible arrows, but that is one reaction, right?
Yeah, I
This is
was
the
kind of having a
synthesis.
hard time. I know you were showing me that there's like two intermediates or
Yeah, there's gonna be two intermediates and three different reactions for this
yeah.
synthesis problem.
So I was like kind of stuck, but
Uh-huh.
I feel like I mean, I guess maybe my question is like why wouldn't that work?
Why wouldn't this work? Yeah,
Yeah.
because if I put, let's say, H2SO4 and water right here, the first step you did is correct. We protonate the alkene and we get the more stable carbocation on the more stable position, which means the less subcarbon is going to get protonated, giving the more subcarbon the carbocation right here. Right,
Okay.
so that's good. Then, whenever we form this carbocation intermediate, we always look out for the carbocation rearrangement step, like either a hydride shift or methyl shift. In this case, it's good. We don't have to worry about that because it's already in its most stable position, tertiary position, right? It doesn't want to become a primary carbocation, secondary carbocation. That's good. So the next thing you do is correct, right? We could either use HSO4 minus or water as a nucleophile. And why do we use water as a nucleophile rather than HSO4 minus, even though there's a full negative charge on the HSO4 minus right there?
Um, because like I think H2O is like more able to react, and like yeah, there's a lot of like bonds and I think resonance.
Yes, resonance. That negative charge on this oxygen here is able to do a lot of resonance due to the double bonds nearby. And because of that, this negative charge is more stable, aka less reactive, right? Less nucleophilic, weaker nucleophile, right? Whereas if you look at the pairs of electrons at that oxygen right there, It's localized. There's no resonance going on. Right. So that's why this right here will be the nucleophile, which is going to attack that carbocation and give us this intermediate right here, where if I star the nucleophile atom oxygen right there in purple and dot my electrophile carbon right there in purple, this is the carbon being attacked. This is the new bond. This is the oxygen right here that I starred. Right?
Okay.
On your answer, you attached the oxygen to that carbon right here.
Oh.
Right? But we did not attack that carbon. We attacked the carbon right here, the tertiary carbon, this purple dot carbon right here, not this carbon right there. Right?
Okay.
And now this oxygen right here has two hydrogen bonds, so I'm gonna draw them out like this. One like that, and I like how you draw the other one out with its bond explicitly like this, right? Because what would be the formal charge of this oxygen with three bonds? One,
Plus.
2, 3, plus charge, right? So if this was a mechanism type of problem, don't forget about that plus charge, formal charge.
Oh, right.
So now the next step is correct. You could use either helix, doesn't really matter, water, or HSO4 minus as the base, right? In this case, you used water, but you could have also used HSO4 minus as the conjugate base, which would make this H2SO4 the acid catalyst, right? Because the definition of a catalyst is that it gets reformed in the mechanism. If we use HSO4 minus as the base, we are going to see that acid catalyst in effect, right? Because this HSO4 minus here, when it grabs the hydrogen, it becomes H2SO4 again, right? And at the same time, this bond here between the oxygen and hydrogen, those two electrons are going to break and go into that oxygen to give us not that product, but this product right here.
Okay.
Right. And there's no bond right here. Right. The mistake that you had on your mechanism was that you attached this OH2 plus oxonium ion on the wrong carbon. You attached it to this carbon right here. Right.
And
But-
we're saying that we couldn't attach it. Why?
Yeah, we couldn't attach to that carbon right there because that's not the carbon that this
The
this water
carbocation.
attacks. Right. This water, oxygen here, attacks this carbon right here.
Right, and
The
it
purple dot
forms
carbon.
a new bond.
Yes. Which is this new bond right there. Right. Not this right here. Right. Because this is not the carbon being attacked. Right? Nothing happens to that carbon. That carbon, nothing touches it. So it has to stay untouched throughout the whole mechanism, like that.
Okay.
Right. So that is hydration of alkene, where you have H2SO4 with water. You're gonna add the nucleophile on the more sub position, more Markov position right there. Right. Okay. So now let's go back to the original synthesis problem right here, and let's go backwards. Let's do retrosynthesis. You learned about hydroboration oxidation already, right? Like the reaction where it adds alcohol to the less sub side, anti-Markov composition. So let's go
Yeah.
backwards. Right. Let's say that this alcohol here attached to the anti-Markov composition, because you see how this carbon here is at the less sub position compared to this carbon. If we go backwards, let's say our alkene was right there, right? And we added our alcohol on this carbon here, the less sub carbon, aka the anti-Markov composition. What reaction do you know that can add an alcohol at that less sub anti-Mark position?
Was it that the new one, the oxymercuration?
Oxymercuration demercuration is going to be the opposite one, the enemy of that one. What is the enemy of oxymercuration demercuration? It's another long name. Starts with an H.
Is it hydroboration something?
Hydroboration oxidation, correct.
Yeah.
Right, and that requires two steps. First step is gonna be I forgot, like BH3, THF,
THF or NaOH in water.
NaOH water. Th- that's gonna be probably the second step, right? NaOH,
Mm-hmm.
water, and then hydrogen peroxide, H2O2. This is the most important thing because that's the thing that allows it to become um, anti-Markovnikov, right? Where we add the OH on the less sub position. Most reactions that you see in alkene here is Markovnikov, right? We add a nucleophile on the moist sub position. There's only like 2 anti-Markovnikov reactions you'll see in this alkene section. The one we just did, hydroboration oxidation, which adds alcohol to the less sub position, and radical addition of HBr. Right, when you see HBr with ROR, you're gonna see that next week. You're gonna add bromine to the less sub position, right, with ROR. If you don't see ROR, then it's going to do the normal HX reaction, right? But does this make sense so far on how we got this alkene going backwards?
Yes.
Yes, okay. So now we have to try to figure out how we can create this alkene from this alkene right here. What are one of the reactions you guys learned that can form alkenes at the beginning? Like, what are some reactions that can form or synthesize alkenes?
Like our regular E2, E1
Mhm.
reaction?
Yeah, like a regular E1, E2 reaction, elimination reaction. So let's think about it like this. Let's say that this came from an elimination reaction, right? Where this carbon here in pink had the leaving group, right? Because that carbon that I just color coded in pink has, like, is shared with that alkene right there. So if I go backwards and I put a halogen like right there, like a good leaving group, like bromine, what kind of strong base do you guys think we used to convert this haloalkane into this less subalkene, right? Because we could have formed an alkene here, here, or here, but we decided to make the less stable alkene, less substituted alkene. What kind of E2 reaction does that suggest?
LDA or tert butyl?
Yep, like a bulky base Hoffman E2 reaction. You could either use LDA or tert-butyl, right? That's gonna form your less subalkene, right? Because it's gonna choose for the most available hydrogen, aka least substituted beta hydrogen, right? LDA is gonna grab that, make a double bond here, kick out the leaving group, right? If we used NaOH, like a small base, that's gonna grab the most substituted hydrogen, make a double bond there, the most substituted one, and then kick out the leaving group, giving us this more substituted alkene, right? But we don't want that because we want to eventually get to here, right? Now, what reaction do you guys know that can convert this alkene into this haloalkane right here? What reaction adds a bromine at this Markovnikov position, more substituted position?
Would it just be a regular HBr or no?
Yeah, it would just be a regular HBr, addition of HX, where the X in this case is Br, right? Or you could think of this as hydrohalogenation, where we add the halogen on the Markovnikov position of the alkene, like that, right? So this synthesis problem here had 3 reactions in total. The first reaction, addition of HX or hydrohalogenation. The second reaction we did, E2 Hoffman. Third reaction we did, hydroboration oxidation, which is one of the newer ones that you guys just learned about last week. Right. Any questions on this synthesis problem or about the reactions or the thought process behind it?
No, I think that makes sense.
That's good. Okay. Layla, did you have any questions or problems you want us to go over tonight?
Honestly, I was mostly confused with synthesis too, and on
Uh-huh.
like NMR, so I feel like this is a good start for me, but
Yeah.
NMR is also kicking me.
Oh, NMR, right? Like HNMR, like those problems. Yeah. I see. Um, do you guys want to try another synthesis problem? Or Elisa, did you have like another like problem you want us to go over?
I don't have any
Uh-huh.
in mind, but if
Yeah.
you do have any example,
Uh-huh. Yeah, let's do another synthesis problem, and after that, can you guys send me the winter 2024 exams? And we could try out the synthesis, I mean, NMR problems there. Because like I forgot those, and I'll show you guys my thought process on the NMR problem. Okay. So one of you guys can send it to the Zoom chat or email or Discord while I make a synthesis problem here. Let's see. What reactions did you guys learn? This is a good one here. Okay, try this synthesis problem out, and then we'll go over it. There's gonna be multiple correct answers for this one here. Two different pathways I see right now. And you guys learned about these reactions already, so you guys should be able to do this one. And I'll give you guys a hint. There's gonna be some major 118A reactions here, like towards the end of 118A. How's it going so far? Are you guys halfway there, still working on it, or finished?
I'm low-key completely stumped. Like, I can recognize one thing, but otherwise,
Mm-hmm. What is that one thing that you recognized here?
I know there's an addition of carbon, so there has to be a Grignard.
Mm-hmm. Yep. So let's go backwards here. Where this new addition of carbon bonds is going to be the Grignard reagent, and this carbon here that is holding this alcohol used to be the carbonyl carbon, right? So if you go backwards, and we put a carbonyl right there or a carbon double bond oxygen right there, this alcohol OH here came from that carbonyl oxygen, right? Where the carbon that I just dotted in red is that carbonyl carbon right there. So that means the Grignard reagent would have been that starred carbon that I just starred out. That carbon is attached to the MgBr, right? Because the carbon directly attached to the MgBr is partial negative charge, making it the nucleophile, which is going to attack this electrophilic carbonyl carbon, popping the double bond onto the oxygen, which gives it an O minus. But then we could protonate that O minus and make it neutral by adding in a second step of acid workup, H3O plus. Right. Where this right here is the new bond between the star and dot carbon, the new bond between the nucleophile and electrophile. Right. Did you get this as the last step when we go backwards here, or did that make sense for you?
Yeah.
Mm-hmm. Okay. So now, oh shoot, I just realized. Okay. So now, okay. What do you guys notice here? How can we convert this into this? And now I know like there's like three different ways that we could do this. Like looking at this not right now. There's actually a shorter way, and then the original two ways that I like intended this synthesis problem to have would be the long way, but I just recognized a shorter way here now. Uh-huh. What ideas or reactions do you guys know that can, let's say, convert this into this? But it's not going to be one step. Like, we can't do this in one step. Right? Like, you guys could either think going forward to this is, or you guys can think going backwards. Like where could this carbonyl could have came from, right? Where did this carbonyl come from?
Was it possible that it was oxynucleation? Not sure.
Oxymercuration, demercuration. So oxymercuration, demercuration would add alcohol to the moist position, right? So let's say that it did come from an alcohol, right? Because oxymercuration, demercuration would add alcohol or OR onto the Markovna composition. So let's say this was the product of the oxymercuration, demercuration from the alkene later on. But going backwards here, we could have said that this carbonyl, carbon double bond oxygen, could have came from this alcohol OH right here. What reaction in 1:A do you guys know that would convert this OH into this carbon double bond oxygen here? There's two reagents that you could do here based on this secondary alcohol.
Jones.
We could use Jones or PCC, doesn't matter, right? Because we're doing oxidation here. We're gonna oxidize this secondary alcohol into this ketone, right? And we could do that by using Jones or PCC, does not matter. It would matter if it was a primary alcohol, right? A primary alcohol with Jones would get a carboxylic acid. A primary alcohol with PCC would end at a aldehyde. But secondary alcohol with Jones or PCC would get to that ketone right there. Right, so that's oxidation. And the way that I intended this problem to be is like to use either oxymercuration, demercuration, like Elysia suggested, or hydroboration oxidation, right? But that would be like the longer way, like looking at this right now, right? So let me just give you guys the short way. We can convert this bromine into that alcohol by first doing SN2 reaction with this acetate, making an ester right there. And then once we have this ester, we can convert that ester into the alcohol by doing ester hydrolysis. So do you guys remember back in 118A where like they just showed you guys this reaction for some reason, converting like this ester into this alcohol, using these reagents, but they didn't show you guys the mechanism because they said this is a 118C mechanism. You won't have to worry about the mechanism here. This is basically what we're doing here. Right. What's the problem here? Like, why can't we use NaOH and water directly from this haloalkane and to this alcohol right here? Like, some people might try doing OH minus, attacking that carbon, kicking out the bromine, but that would not happen. What's the problem here? What reaction would happen instead? If we have a secondary haloalkane, OH minus, strong base, strong nucleophile, small, good leaving group present, right? So what kind of reaction would happen there? SN2, E2,
SN2?
SN2
Or
if it was a
E2.
primary substrate, yes. This reaction here, because we have a strong base, strong nucleophile, always associate that with E2 if it's not primary, right? Because this is secondary, we're gonna do E2. We're gonna form an alkene instead, which is that alkene right there. Right, because this is the good leaving group right here. This is our alpha carbon. These are our beta carbons. If I draw out one beta hydrogen for each beta carbon, let's say this is beta hydrogen A, beta hydrogen B. Because we're using NaOH, a small, strong base, strong nucleophile, we're going to go for the Zaitsev E2 product, meaning that we're going to go for the more substituted hydrogen, A, make a double bond there, kick out the leaving group to get that more substituted alkene, the Zaitsev alkene product, right? So we can't do SN2 here, E2 would result instead, right? So that's why we have to do SN2 with this acetate ion, substituting this bromine with that ester. And then once we have this ester, this is a 118C ester hydrolysis reaction. We convert that whole ester into OH by using like NaOH and water, right? So that was a 118A thing. But let's say that you did do NaOH and water, which gets you this more subalkene right here. What reaction can we do to convert that more subalkene into this intermediate right here, that alcohol, right? There's one reaction we could do here. And this is going to be one of the new reactions that you guys just learned and we just did in the last synthesis problem.
Is it still the hydroboration?
Hydroboration oxidation, because we notice that the alcohol here is on the less sub side of the alkene, the anti-Markovnikov side of the alkene. So that is a sign of hydroboration oxidation. First step, BH3THF. Second step, NaOH, water, and H2O2. Okay, so that was the intended synthesis route that I wanted to give you guys. And looking at it right now, it's pretty equal, right? So I was gonna say that's the longer route, but it's equal because that's one step, two step, and this was also one step, two step. So they're equal steps right there. There's one more route here, right? Which is gonna be like if you reacted this with LDA, you're gonna go for the Hoffman alkene, the less substituted alkene right here. And how can we create this alcohol from this alkene right here? What reaction do you guys think we could use here?
Is it the oxymercuration?
Yeah, oxymercuration, demercuration, right? Which the first step is gonna be Hg parentheses OAC to, in this case, water. We have to use water here, not alcohol, because we want to add alcohol, OH, as a product. So we have to use water as a product. I mean, as a reagent. And then THF. Second step. What was the second?
NaBH4.
Okay. NaBH4 reducing agent. Yep. NaOH water.
Mm-hmm.
Right. Okay. So why did we have to use oxymergration demigration? Why couldn't we use H2SO4 and water? What's the problem there if I used H2SO4 and water?
Is it that there's no carbocation rearrangement? Or like no rearrangements?
Yeah, we don't want to do any carbocation rearrangement at all, right? We see that we added alcohol directly on that moist carbon of the alkene, like that. If we did H2SO4 and water, there's going to be a carbocation intermediate, and then whenever we form any sort of carbocation intermediate, we always stop and look out for any rearrangements that we could do, like a hydrogen shift or methyl shifts, right? And then there will be one here creating a carbocation at this more stable position, which the alcohol is going to attach there instead, right? But we do not want this alcohol, right? Because this alcohol here is tertiary alcohol, and we cannot oxidize a tertiary alcohol, right? If we use Jones or PCC there, no reaction is going to happen, right? We want the alcohol here, so then we could oxidize that alcohol to this ketone, and then we want that ketone there, so that we could do this green reagent, getting to this final product right there. Right. So there are three different routes here that you could do: the red route, blue route, or pink route here, and they're all equal steps, equal amount of steps. Right. The red route is like all 1:A reactions. Like every single reaction in the red route is 1:A. The blue and pink route is 1:B. Some 1:B reactions. The beginning part is 1:B. Right. Any questions on the synthesis problem or any part of the routes here?
Would you say that this would be a typical style of helix?
Yes, because helix synthesis are typically around 3 to 5 steps. Like 5 is pushing it, 3 to 4 steps is average for his helix.
And then,
like,
do you think he would expect us to do the purple or like the blue or pink route instead of the red, or?
Yes, especially for the first midterm.
Yeah.
He would prefer you to do the blue or pink route, but if it works, he can't take points off of that for that, right? Like if you do the red route, like you still get 100% for that, even though it's all 1:A, right? Because synthesis is like kind of creative. Like you could use any reaction you learn as a tool in your toolbox, and then if it works, it works. But make sure it's high yield, because some reactions would like make it low yield, and if there's like a lot of steps, like if you have another synthesis route which is like a lot of steps, that makes low yield and you get points off for that, especially for leave-ins. But in this case, all routes had the same amount of steps, so they would all get 100% in this sort of reaction, right? But he'll probably design the synthesis problem in a way where you have to use at least one alkene reaction that you learned for the midterm one.
Okay.
Right. Okay. So let me go over this spectroscopy problem with you guys. Right. My approach to spectroscopy problem are these 5 steps right here. There's gonna be different approaches, like based on who you guys ask, like TA, professor, or another tutor. They might do it differently, but this is how like I'm used to doing it. The first thing I always do is I always calculate the degrees of unsaturation, DOU. Second step, after that, I always look at the IR for what functional groups are present in the unknown molecule. After that, the third step is I look at the HNMR, and I start forming my fragments based on the peaks, subpeaks, and like the region, de-shielded, shielded regions. The fourth step is then I start connecting the fragments, and that's probably the hardest step, right? And pray, right? Because there's a lot of trial and error here. Trial and error, right? The like first time you're gonna do this, you're gonna probably mess up a lot. and make a lot of mistakes, but that's when you go back and check and like retry something else. It's like the puzzle, right? Like start making new fragments, start connecting the fragments in a different way. So this is the hardest part, step 4. The last step 5, is you verify with all the tools they give you. The chemical formula is a powerful one to keep track of how many atoms you use, like how many carbon atoms you used, how many hydrogens, how many oxygens, nitrogens, halogens like bromine, chlorine, iodine, etc. DOU, IR functional groups, HNMR, and I'm gonna put this in parentheses, CNMR, right? Because I never used CNMR for these synthesis problems. And you could basically solve the unknown structure using just the IR, HNMR, DOU, and chemical formula, right? I've only seen one synthesis problem, which was for Levin's class, where you had to know CNMR to tell the differences between the correct structure and the structure that's very similar. But for Helix's class, we probably don't need to use CNMR to solve the unknown compound, right? So let's start with this spectroscopy problem here. The chemical formula is C11H14. The first step, calculate the DOU, which is 2C plus 2H. Oh, no. Wait, what? I forgot the formula. 2C plus 2 minus H minus X plus N all over 2. Right. So that's going to be 2 times 11 plus 2 minus 14. 0 halogens, 0 nitrogens, all over 2. And that's 22 plus 2, that's 24. 24 minus 14 is 10. 10 divided by 2 is 5. 5 degrees of unsaturation. Right. Wait, is this? This is midterm 2. Wait. This is midterm 1 or 2? Here. This is midterm 1? What? Okay, that's interesting. Okay. So if there's more than 4 DOU, what functional group do you guys think is going to be present in an unknown compound here? If there's more than 4 DOUs.
Isn't it a benzene ring?
Yeah, benzene ring, right? And to check that benzene ring, do you guys remember what region the benzene prefers to is going to be in the HNMR? Like between what ranges, what ppm range? I'm gonna make sure this is actually benzene. Two, three, five, yeah. 1.
Is it the 6 to 9 range?
Yeah, 6 to 9 range, which is gonna be here. But there's 6 hydrogens here, so I'm getting a little stumped right here. So let me actually work this out and talk this out with you guys here. Okay, so okay. I'm gonna skip that for now and then move on to the next thing. When I get stuck, I just move on to the next piece of information they give us, and then hopefully it makes sense later on. Right. So the next thing I'm gonna look at is IR. So let's look at the IR here. 1500 and below fingerprint region. Ignore that. We see a sharp peak here at around 1600. What functional group is present at 1600 sharp peak? You bring out the IR chart here, right here. Yeah. And Helix will give you a chart of IR values for your exam, but it's gonna be like this form, right? Like what functional group is present, like what kind of bond is that, and like the wave number range for the IR. You could use that chart, but I'm gonna use this one right here, where at 1600 we see a sharp peak, which represents the alkene functional group, C double bond C, right? So we have an alkene present in the unknown molecule. At 3000, right, that's the regular sp3 carbon hydrogen bond. Right, so we could basically ignore that because that's just the regular like carbon hydrogen single bond. That doesn't tell us a functional group, but this alkene does. So on the IR, all we got is that there is an alkene present on the unknown molecule, right? CNMR, I won't look at that for now because I don't think I'll need that. Now let's go back to the HNMR. We have coupling constants here. You get to give that as the J values. Which are these J values here. So let's draw an alkene out as a template, which we know is present. And let's figure out the relationships between these hydrogens here. We see D and E have matching J values of 11, right? Which is going to be around 10. So that means that they are cis to each other. So I'm going to draw hydrogen D out like that, and then hydrogen E out like this, right? Cis to each other, right? Cis on the same side of the alkene because they have a J value of 11, which is around 10. And I know there's one D hydrogen and one E hydrogen because of the integration on the HNMR here. So that checks out the D and E peak. Right, so I'm going to cross out that peak and this peak right here. Right. Okay. So we use that, and now you're ready. Now, we see that E and F have matching J values of 6, which is going to be, there's no name there, but I'll call that the alpha relationship, right? Because this is the alkene carbon. The first carbon away from the alkene carbon is the alpha carbon. If you look at this alkene carbon and the alkene hydrogen right there, this hydrogen right here is the alpha hydrogen relative to that hydrogen right there, right? Because it's on the first carbon away from the alkene. So to represent that, I'm going to draw HF right here. And how many HFs do we have? We have one HF. HF like that, right? The reason why I did not draw HF here is because HF is not alpha to HG, right? HF is alpha to HE, right? So that's why I drew it on this side, the HE side.
Wait, could you repeat that one more time why it's on that side?
Yeah, it's going to be on this side because we see that HF and HE, based on the J values, they have a matching J value of 6, right? And if they have a matching J value of 6, we look at the typical J values chart, which means that HE and HF are alpha to each other, right? Meaning that if this is HE, then HF has to be alpha to HE, one carbon away from the HE, right? If I put HF right here instead on the left side, HE here and HF would no longer be alpha to each other, right? They would be actually allylic to each other, right? Where if you think of this as HE right here, like this hydrogen here as HE, this other carbon here on the other, this hydrogen here on the other side of the alkene, like this is still the alpha carbon, but it's not alpha to the same carbon as this H right here. It's allylic, right? He calls that the allylic relationship. Right. So to understand that better, let's understand the differences between this and this right here. I'm going to highlight the alkene hydrogen in yellow like this. This is the alkene hydrogen. This is the alkene hydrogen. And then I'm going to highlight the hydrogen that is, like, we're looking at the relationship with this yellow hydrogen right here. We see that the alpha hydrogen here is coming off of the same carbon as this yellow hydrogen right here for the alpha, pink hydrogen, right? But for this one down here, this pink hydrogen is on the opposite carbon, right, on the other side of the alkene. Right. They're both alpha carbons or allylic carbons, but this one right here is on the other end of the alkene, whereas this one here is on the same end, same carbon as this yellow hydrogen right there. Does that make sense? Like the differences between this alpha relationship and this allylic relationship here?
Yeah, that makes a lot more sense. Thank you so much.
Yeah, and because of that relationship right there, we want HF to be on the same carbon. I mean, the alpha carbon has to be on the same carbon as the HE, right? If the HF was right here, that means the alpha carbon here would be on the opposite carbon of the alkene, right? And that would not make them alpha to each other. That would make them allylic, and that means that they would have to have matching J values of 2 instead of 6, right? 2 right here to represent that allylic relationship. But we have 6. So HF has to be alpha on the same carbon of the HE right there. Right. Okay. And we see that we only have one HF, right? One HF available. So that's one fragment, and this is another fragment right here, right? Because this carbon here has to have like 4 bonds to be neutral. And because we only have one HF, these are our 2 fragments that I don't know what that's attached to yet. It could be another double bond, right? Like this could have been another double bond here, or it could have been like a branched molecule like that. I don't know yet, right? Okay. But now let's look at HF right here, which is between 2 to 3. 2 to 3, looking at the IR right here. Oh, HNMR? Wait, I didn't. I think I showed Elisa already, or let me ask both of you guys. Are you guys familiar with all the HNMR regions, like where everything is based on the regions, like on the ppm range?
Yeah, kind of.
2 to 3, right? If you remember, is the alpha region, like the first carbon away from an alkene or double bond, right? And that makes sense because we see HF right here is on the alpha carbon of this alkene, right? Which is why it shows up right there between the 2 to 3 region, alpha region. But now let's look at the number of neighbors here. This AF here will have 1, 2, 3, 4, 5, 6 subpeaks, meaning that it will have 5 neighbors, right? Because neighbors is going to be equal to subpeaks minus 1. So right now, as we have this fragment out, this HF right here only has 1 neighbor, which is HE. Right. And that means that we're missing 4 neighbors right here. 4 neighbors. And it could be a whole bunch of combinations. It could have been like this, right? Where it's 3 other neighbors are here, 1, 2, 3, and its other neighbors right here, right? So its 5 neighbors would be 1, 2, 3, 4, 5, like that. Or it could have been something like this, where its 5 neighbors are 1, 2, 3, 4, 5, like that. We don't know yet. We don't know exactly what it is yet, but we do know HF has 5 neighbors, right? So I'm gonna leave that alone for now because that's gonna get too messy, and then I'm gonna move on to a different fragment. But I'm gonna keep in mind that HF has 5 neighbors. Now let's look at this 6H right here. When you guys see a 6H with a doublet, do you guys remember what common fragment that shows on from when it's in A? Like what common?
Yeah, it's isn't it like a two methyls attached?
Isopropyl, like
Yeah,
this.
isopropyl.
Right, where the 6 hydrogens are gonna be these 6 hydrogens right here. 1, 2, 3, 4, 5, 6, with 1 neighbor, right? Its 1 neighbor is this 1 hydrogen right here. Which is why this is a doublet, right? Because 1 neighbor, 1 plus 1, 2. So we know we have an isopropyl somewhere in the unknown molecule, right? And make sure to draw those fragments out in this box because you get partial credit for that. You get majority of the points by drawing out the fragments that you have. The hardest part is like writing the proposed structure, connecting all the fragments into the specific unknown molecule, right? Okay, so let's look at hydrogens A, B, C here. This is the ones that's tripping me up right here. Because this is the benzene region. So let's just add a benzene right here. Right? 6 to 9. Even though hydrogen D is between 6 to 9, we know hydrogen D is not going to be benzene. Hydrogen, because it is cis to hydrogen E, so it has to be an alkene like that. Right? And we have 2 hydrogens here, 3 hydrogens here. That's 5 hydrogens total. So that means that this tells me that this is a mono-substituted benzene ring. Right? There's one substituent on that benzene ring, giving us 5 benzene hydrogens. 1, 2, 3, 4, 5 benzene hydrogens like that. Yeah, right. So I'm gonna say that we have a mono-substituted benzene ring just because of this like 5 hydrogens right there at the benzene area. Okay. Now I'm getting stuck here, so what I'm gonna do now is that I'm gonna count how many carbons I used up. We know we have 11 carbons in the formula, so we used up 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 carbons right here and fragments right there. Ooh, okay. So what I'm gonna do right here is I'm just gonna connect this isopropyl right here to that fragment right there, and that's gonna give me one of the combinations that I gave you guys earlier. So I'm gonna make the alkene like that, and put an isopropyl right there, making this a methyl group right there, right? Where this is HD, this is HE, this is HF, like that. Right. Where this HF has 5 neighbors. 1, 2, 3, 4, 5. Yep. Isopropyl is right here. But we have these 3 hydrogens with 1 neighbor, which should be a quartet. But I don't see any 3 hydrogens here with 1 neighbor, so that does not make sense right now. This is getting weird here. Let me see. Let me add a benzene right here. Okay. 2H3H isopropyl right here. See, now I'm just like trying random things. I don't know if this is gonna work, but I have like the general idea of what the substitutes are. Like I know I have an isopropyl group, maybe a benzene ring, and this sort of alkene right here, like on the end, right? Wait, hold on, but there has to be something here though, because there's only 1 HD. So there's gonna be another fragment here. Let me expand this fragment really quick. Okay. I'm just gonna work on this for now, and then explain it later on, because I don't know what this is actually yet. HD. Let's put benzene like that. Like that. HF. Let's put isopropyl right there. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Too much. Too many carbons. Let's do this instead. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 carbons. 14 hydrogens. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14 hydrogens. Okay. 5 DOU. 1 plus 4, 5 DOU. Okay, this is looking promising so far, but let me see here. HD, HE, HF. HF right here, it has 1, 2, 3, 4, 5, 6, 7 neighbors. That's too many neighbors here. But I'm just gonna say that 1, 2, 3, 4, 5, 6. It should have 9 suffix if there's 1, 2, 3, 4, 5, 6, 7 neighbors like that. I mean 8 suffix. Right. 1, 2, 3, 4, 5, 6, 7, 3, 6. So it should have 8. 1, 2, 3, 4, 5, 6. Okay, I'm just gonna stick with this because that's the only thing that makes sense for me right now, and say that this is 8 subpeaks somehow. 1, 2, 3, 4, 5, 6, 7, 8. Right? Because we have our isopropyl here. Our one hydrogen is right here, which would match up with this one hydrogen right here, right? That has a ton of neighbors. And it's alpha to this alkene right here. And this alkene right here is on this mono-substituted benzene. And we know it's mono-substituted because we have 5 benzene hydrogens right here between 6 to 9. Right? So to have that 5 benzene hydrogens, we only have to have one substituent to allow for these 5 benzene hydrogens right there. And this right here would satisfy all of the atoms in the chemical formula, 11 carbons, right? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and 14 hydrogens. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14 hydrogens. And our 5 DOUs, 1 from this alkene, 4 from this benzene, that's 5. And then this alkene here satisfies all of the J values here that were given, right? So I don't know if this is right, but my final answer here would be this benzene with this alkene that is cis and that isopropyl right there. Can you guys check the key for this one for me? And if it's wrong, we'll analyze like what I did wrong and how the correct answer is correct, and how that would make sense instead.
I think that is right. Yeah.
Oh, this one is right?
It says the fragments were aromatic rings, cis alkene isopropyl group. I think that it looks. Oh wait.
There's probably something wrong with this HF right here because it looks like there's 5 neighbors, but this HF I have right now has 7 neighbors. 1, 2, 3, 4, 5, 6, 7 neighbors, which is like way too many for this amount of subpeaks.
But I think that looks about right.
That looks about right. Like, can you send me a screenshot on Discord on what the key looks like?
I'll send it to you right.
Thank you. Yeah. Because if this is right, then this HNMR problem was mean because the number of subpeaks for this peak right here, HF, should be showing 1, 2, 3, 4, 5, 6, 7. It should have 8 subpeaks. But right now we see it like 1, 2, 3, 4, 5, 6. 1, 2, 3, 6 subpeaks.
Okay, I just sent it. It looks about right.
Oh, yes. So the way that he drew it was like this benzene right here with this cis alkene coming off of it and isopropyl right there, which is the same thing as that. Right, so that is correct. But this was a difficult one because I don't agree with this peak right here because this peak should have 8 subpeaks if that's the right answer. Right. I don't know if I printed out weird, but like you could say that's 1, 2, 3, 4, 5, 6 subpeaks. And I don't know if you guys can see this, that the little tiny speck right there. I don't know if he counts as a subpeak. That's really mean if that counts as a subpeak.
Yeah, that was mean.
Yeah. Yeah, that's why I was getting stuck because of that this one specific peak right here. H. Another way that you can confirm it is that you know how like we were able to find out the common fragment of this 6H doublet, which is this isopropyl right here. That means that we have to have one H that has a lot of subpeaks, right? Because this one H right here has a lot of neighbors right here, which is gonna correspond with that one H right there. So that's another way that you can confirm like that.
That makes sense.
And why is it between 2 to 3? Like what makes it between 2 to 3 here? Like let's say this is HF. What environment makes this HF between 2 to 3?
Is it because it's de-shielded?
It's a little bit more de-shielded than the regular single bond that is not next to any functional group at all or electronegative atom. It's de-shielded because it's alpha to something, alpha to like a pi bond, right? Like we see this HF here, it's right next to this double bond right there, right? And we call that the alpha carbon, the alpha region between 2 to 3. Right.
Okay.
Like this HF right here, you notice how it's on the alpha carbon or the allylic carbon, like away from this double bond right here. That's the alpha region right there, 2 to 3, right? Because on the HNMR, if you see anything between 2 to 3, that's the alpha region, meaning that your hydrogens would be alpha to some sort of pi bond, like that, or it could even be triple bond like that, or it could even be a alkyne like that. But we'll worry about alkynes for midterm too. But when you see a peak between 2 to 3, that's the alpha region, meaning that that hydrogen is going to be on the alpha carbon, the first carbon, away from a pi bond, a double bond, like alkene or a carbonyl, like that, right? Which we do see here. HF is alpha to this alkene right there. Right.
I see that.
Yeah. So just think of this as like ballpark regions, because you know how like this H right here, HD is like going into the 6 to 9 range, which is benzene hydrogen. We see that HD right here, HD was not a benzene hydrogen at all. It was an alkene hydrogen, but you notice how this alkene hydrogen here is also like alpha to this benzene right here, like next to that benzene ring.
Yeah.
That's what makes it more de-shielded, more to the left side, right? If that benzene was not there, and let's say that was like a regular alkane right there, then this peak right here would be more between 4 to 6, like around 5 to 6, the alkene range instead, right? But the reason why it got bumped up or shifted more to the left side, the de-shielded side, is because it is right next to this benzene right there.
Okay, that makes sense.
It would even become more de-shielded if there was like electronegative atoms like oxygen, fluorine, bromine, like that. That would even shift it more to the left, like that. More
Okay.
de-shielded, right? Okay. So we could practice more NMR tomorrow and finish up the reactions of alkanes in tomorrow's office hours. But you guys have any questions about this process?
No question. Just more practice, yeah.
Yeah, let's practice. I know. Like spectroscophy, like you know how I like was stuck at some points and then I got lost, but then I like hopped around different information,
Yeah.
puzzle pieces, and then like I just like start making random stuff up at the end and started praying it just started hoping it works.
Yeah,
And
trial
then
and error.
trial and error, and then I gave up on trying to make the one hydrogen make sense with the 6 suffix we saw, and I just like YOLO'd and said like that's that H right there, which worked out.
Yeah.
Yeah.
Thank you so much, Brian.
Of course, Elisa.
Thank you so much.
Of course, Leila. If you guys come tomorrow, feel free to email me, send me a DM or school message on what you guys want to go over, so then I can like go over that tomorrow as well ahead of time.
Is it the
Okay.
same time as today?
Yeah, same
Or-
time,
oh.
9 to 10 p.m.
Thank you so much.
Thank
Yeah.
you. Have a good night.
Of course. Have a good night, guys. Bye.
Bye.
See ya.
See ya.